Hey there, everyone. Welcome to another session of Global Hack Week. Today, I will be your coach in charge of this stream. We're just getting started with day 3, so we still have a lot of content to share with you, especially for Beginners Week, which is usually where new hackers or people just want to start fresh. As it's January and we're just getting started, maybe you just want to prep for hackathons or start that cool new project. We got you. For today, I'll be giving another session on hardware hacks. So for this Global Hack Week, we already saw introduction to Arduino, where we got to learn a bit about motors. Then for today, I'll be teaching you how to make your robot balance, or most specifically, learning about PID controllers, which is something that really comes up when talking about robotics and control systems. So if you are getting into hardware and robotics, you will definitely get to see a lot of these in here. Please don't forget to check in on the stream, because this is your way of getting points for the weekend. And in that way, we can count attendance of who attended which streams and was there present. There's a question over here. I'm new in MLH. Can you tell me how to do challenges and submit them? Yes, of course. So I'm gonna share you the link where you can find all of the challenges. Oh, sorry, I sent the incorrect link. That's the checking link. And then this is the other link for checking the challenges. Because in there you will basically see like a grid of all of the challenges that you can apply to. I was looking for the short link, but you can also find that one in there. So this one is for the challenges. And then for submitting them, it's just you check the challenge that you want. So for example, right now I'm on the same link that you shared. And let's say I want to fill out the address form. So I click on address form, and then I have to fill out like that type form, and then that's it. But then there's other challenges, like for example, let's say portfolio website, showcase yourself to the world. And then there's a button in there that says submit your project. If it doesn't say that you need to submit anything, that means that only by doing the thing that it's asking you, like for example, linking your Discord account to your My MLH account, and then you should be good to go with that. Let me know if you have any questions as well. Day one's points, update email, see yesterday, when will today will come out, about day 2. Not pretty sure. I guess this time around the morning they are usually sent out, but keep pending in your email, and if you don't receive anything, feel free to open a support ticket on our Discord channel. How does this work? Would you mind explaining a bit? What do you mean by work, like the challenges, Global Hack Week, MLH? Like I have just registered, even I got to know about MLH now. Okay, yeah. So if you just register to your to the Global Hack Week, then you will realize that there's a schedule that you can see of all the streams that are going on. So if you go ahead and access this link over here, you will see all of the streams that are going on and all of the schedule for the rest of the week. And then on that same page, you can also see the challenges. You can also see swag, FAQs, sponsors, and then you can also join like our Discord in there as well. Okay, so I guess we are good to go into getting started. So if there's any questions, feel free to drop them on the chat. I always check the chat. Also, if you want to ask anything like unrelated or related, feel free to drop it. I always enjoyed side conversations, so that's something that I really appreciate. Okay, so I guess I didn't introduce myself. I added some different things to my usual slide because I just wanted to change things. Because I know that some of you already know me and you hear me at basically almost every Global Hack Week. So I'm a coach here at Major League Hacking, which means that I get to travel in order to staff events at other parts. This January, I'll be going to different events in Montreal. I'm going to Mac Hacks in Montreal. Then I'm going to um, TAMU Hacks in College Station. That's down in Texas. And then I'm going to L Hacks in Toronto. So if you're going to be at any of those events, feel free to reach out so we can network. Then I'm also doing some research in neuroengineering. It's kind of a research assistant job. I also study robotics back at Mexico, which is something really cool. I love bee plushies and I collect them. And I'm also a GitHub campus expert. And I was also in the MLH fellowship. That's actually how I got into MLH and all the streaming, coaching, and now being a pod leader for the MLH fellowship. So also, if you have questions about that, feel free to ask them away. Thanks, quite intense because I already completed all the challenges listed there. Oh, that's really amazing. Like every challenges that are there, then I guess just wait for the email. And if you don't receive anything by the end of the day, feel free to open a support ticket on the Discord. Um, Swag depends on points. Yes, completely. So depending on how many points you get on the Global Hack Week is the swag that you can get. I'm pretty sure that there's more information on that on the page that I just shared on the schedule. So for example, I believe there's character stickers, sticker packs, postcards, and the hex stickers that you can get. And then yeah, that gets mailed to your home and you get them. Yeah, so that's also a cool thing. Hey there, nice to see you. All right, so for today we have cool things prepared. So we're mostly gonna be seeing a bit of technical contents, and then I'm gonna be sharing with you a live PID simulation so you can test it out with a motor encoder. And don't worry if you don't understand anything. I'm gonna be going step by step into making sure that that you understand everything. So we're going to be learning about open and closed loops for feedback systems and non-feedback systems. Then we're going to be learning about PID controllers, seeing the math implementation of the formulas. Then we're going to view the code. We're going to learn about encoders. And finally, we're going to do an activity visualizing everything in Tinkercad. So my goal after this session is that you will have a PID class in Arduino for controlling speed in a motor, which is something really interesting. To be honest, this is something that you can then replicate into your own projects. PIDs are basically the base to everything in control systems and robotics. So almost every robot that you will be seeing out there has a PID control system. And you will understand why it is important to have these controllers out there. Okay, so the first thing that we need to see and learn is loops. So there's two types of loop controllers. So the first one is called open loop controller, and this one has no feedback mechanism to correct errors. So it's just a straightforward process, and the control action is independent of the output. That sentence is super important. You must keep it in mind. The action that you do is independent of the output. So let's say, I don't know, in real life, if I were to drop like a glass of water, for example, of course there will be like, I mean, the output is not like it's like independent from the action that I'm doing, because it's not like the floor it's going to magically like catch my glass of water. And then this is a simple controller. It's low cost, but it's also susceptible to disturbances. And some examples of these are, for example, like a microwave. If you see a microwave doesn't care if your food is already heated up or still frozen. Like the actual process of you going to the microwave and telling the microwave, okay, I want to heat my pizza for 2 minutes. And if my pizza is frozen, the microwave, it's only going to heat it up for 2 minutes. And even if my pizza is still frozen, it's not going to like continue heating it up until my pizza is like defrost, right? So this is what I mean by not having feedback. And in here we can see the actual steps. So you receive an input. In this case, it's the 2 minutes that I'm inputting into my microwave. Then we have a controller, which is how the microwave actually works, and the process, which can be a motor or even a system. And then we have our output, and the output is just basically my heated pizza that might be still frozen, because I don't have a way of knowing if my pizza is still frozen or not frozen. And you can also see that more applied into robotics, like a regular motor. Like in a regular motor, you just know that if you turn on the motor will like start spinning, but you don't actually have a way of knowing if your motor is reaching the speed that you really want it to reach. So for classic robotics and just doing simple projects, this is okay. Like it's okay if I just turn my motors on and I make my robot go forward. But when we're talking about industrial systems or more complex robotics implementations, you actually need a way of knowing if your robot is going to reach the end line, or if your robot is gonna behave like according to what you want it. So these are some of the downsides of open loop controllers, that you don't have a way of feedback of knowing if it's really reaching what you want. Open loop controllers, yes, they are simpler to implement and they're also low cost, and there's not much complexity applied to them. So if you're just doing something simple, this is going to work. Like, I don't know, turning on a LED light or switching something on or off, then an open loop controller is perfect for you. But if you want to do something a bit more complex where you want to implement feedback, then we must move on to closed loop controllers. So for closed loop controllers, we are using a feedback mechanism to correct the errors that are popping in there. So basically the output, instead of originally just following a straight timeline, that the output is independent of the input, in here the output is measured and it's compared to the desired input, so what we wish we were getting. And the controller in here is just adjusting based on the error that we're getting. This is much more accurate and it is very robust to disturbances. I will explain that in a second. First, I want us to look at the diagram and see how we are receiving an input in there, and then we are calculating the error. We have the same controller as in the open loop, the same process as in the open loop, but the only difference is that before actually getting an output, we are calculating a feedback in here in base of the error that we just got. Because if you want to measure how bad or how good something is doing, basically measure performance, you need to have an account of the error. So if your error is too big, then that means that you need to correct that, right? And if your error is too small, that means that your mechanism is working and that you are doing your best to like decrease those disturbances that are going on. And then in here, it's just basically the sensor. It can be any sensor. It can be like I don't know, like a force sensor or an ultrasonic sensor that you're measuring like some sort of feedback, which is at the end, it's just another input that you're getting in order to correct your output. So in this case, your output is actually dependent from the input. So they are communicating with each other and they are actually like receiving active feedback. We can see some examples in here. For example, a thermostat, right? So in your house or in your school or at a mall or any other like restaurant or whatever, like they have thermostats in order to measure your like temperature, like room temperature. I actually do not understand Fahrenheit, so I'm just going to use Celsius. So for example, if I set my thermostat to, I don't know, like what's something like for example 25 degrees Celsius, and then I wanted to reach like a specific temperature, like the thermostat is actually like reading the temperature of the room in order to reach that temperature. In difference from a microwave where I only click like 2 minutes and then it heats up for 2 minutes and then stops, even if my food's still frozen. In a thermostat, it is actually measuring the temperature so it can reach the desired temperature. Because imagine that I just place like my thermostat, and the thermostat, like the temperature sensor is not working, then I might just heat up really hot or just be like super cold in my house. So a thermostat is a really specific example of a of a closed loop controller, because you're actually getting feedback from your temperature sensor, which that will go in this case in here. And then in here, we have a question in here. Is that a motor next to the thermostat? Yes, you're correct. So I was just going to go to that other example, more applied into the robotics side. If you can see in here on our first example, I had this simple motor, right? You just turn it on, it goes at a speed. You don't know what speed you're going. You don't know if you're reaching the speed that you want, but you just want them on, and like that's it. But then on this second image, we have a motor, and then we have this green thing with a black like bump in there. That's called an encoder. So the difference between the yellow motor and this motor is that this motor has an encoder. So this motor will actually know when it reached its desired position or its desired speed. So these motors are like more specific, and they are widely used in combination with an encoder in robotic applications for you to know that you are getting feedback from what you're doing. So you're just not turning your motor on, you are actually measuring something, which is in this case our feedback that goes back into the error, which then calculates like our output in here. And no worries if you don't understand these yet too completely. I'm going to be explaining how encoders work in relation to motors further along the presentation. So for now, it's just important for you to know that what we're going to be seeing today is closed loop controllers, and we are going to be focusing on how this feedback loop is working on this diagram in here. All right, so I didn't remember I left that slide. But yeah, so now we're gonna go a bit into what a PID controller is. And before like explaining everything, I guess I forgot to include a slide on why we need PID controllers. So a PID is just something that allows you to like regulate your robot, like make it go more straight, or making it balance, or making it reach like the endpoint that you want. I guess I can look up for some images first, because I don't want to overwhelm you with like all of the constants if you don't have an idea of what it actually means. Let me look for like videos, and then we can see. All right, this one looks really nice. So let me share my screen so you can see it as well. Okay, so for example, in here, I'm just gonna like see if this is working. Okay, so if you see, this is basically just a robot that's standing straight. And if you're seeing them, the person in here is like touching like the robot continuously. And if I were just doing like, I don't know, if you imagine that like my mouse is just like a robot, if I were to do these at a regular robot that doesn't have like any feedback, it's just gonna fall down and it's just gonna like stay in there. But in a closed loop system where you have feedback, if I do this, it's gonna like fix its error, like depending on like how I'm like, poking the robot. So that's why in here the person is like clicking into the robot, and it's still like balancing there. Like the person is clicking and it's still like balancing in there. So the way to do that is by doing a PID controller, which is basically what we're gonna be doing today. So if I do PID, this is another nice example. So for example, if you see this one, this is another PID controller that's like self-balancing the beam. So in this case, the closed loop system goes on the motors that are controlling like the platform. So if this was just a regular platform with no feedback, if the ball rolls to like the edge, it's just gonna fall and it's just gonna go like all the way like this. But these, on the other hand, it's like self-balancing, so the ball doesn't like drop from the station. I guess this is another example. Um, Another example is the PD line follower robot. So this is another example of a PID, a closed loop system. In a line follower, like you mainly just want to, follow the line. But if you don't have a PID, your robot is mostly just gonna move like super awkwardly. But with a PID, you are basically like correcting the error depending on how much black line you're seeing on there, and you're correcting like the direction of your two like rear motors in order to make it move like as smoothly as this person is like making it move like that. Yeah. All right, so hopefully that was enough for you to understand how, the importance of a PID controller in a robot. You can see it as self-balancing like something. It doesn't have to be like literally like balancing a robot so like it can be like standing straight. It can be balancing like different things. It can be balancing speed, it can be balancing angle or direction or position. You can do a lot of things, and you can do a lot of different PIDs, like for example on the line follower or on the balance beam, or there's different kinds. And as much as you get into robotics, you will see the necessity of implementing like these PID controllers. And my goal here today is that you understand what a PID is and how to implement it into a regular motor. So we have some questions in here. We already answered this one. So the encoder chip is used to provide a threshold to the motor. Not so much of a threshold, but mostly just measuring. So it's a measure system that so if you measure something, if you have the ability to measure something, you can estimate performance on that measurement. So that's just how it works. So PID is a decision maker for the robot, like an if-else statement. Not like that. It's mostly just self-correcting. So it's mostly just self-correcting either like anything. So it can be self-correcting your speed, self-correcting your position, self-correcting your angle or direction or distance. So it's not like taking decisions for the robot, like, oh, like if I fall, then I need to like stand back up. You can see it as an if else, yes, because if you are like going very tilted, then you want to like return to your original position. But I wouldn't define a PID as a decision maker. It's mostly just an error correcting algorithm, and you will see in a minute how everything works. So for the PID vocabulary, it's important that we learn some of the variables that we're going to be using. So the first variable is called set point. And now that we saw a couple examples, and I can just go back and refer those examples. So set point is basically the desired target value. So let's take as an example, a simple motor, right? So I have a simple motor and I want that motor to reach 200 RPMs. So that's going to be my set point. So I always want my motor to reach 200 RPMs. And then we have a process variable. So that process variable is a measured current value. So my current RPMs. So when I start my motor, I'm just going to start calculating those process variables like 1 RPM, 2 RPM, 4 RPMs, 120 RPMs, and so on until I reach my set point, which is the 200 RPMs. Then we have the error, which is basically the difference between the set point and the process variable. So it's just calculating a delta between these two. So of course, my set point is like my desired goal. And then we have my process variable, which is like 150 or 20 or whatever current RPMs my motor is choosing. And the error is just basically calculating the difference between my set point and the process variable. And finally, we have my control output, which is basically the signal sent to the system to correct the error. In this case, it's going to be a PWM signal to the motor. I don't want to get a bit into depth on this one on the control output yet because I have an explanation further along. Okay, and this one is just a recap from the previous slide on how to calculate the error. So I'm just gonna type something on the chat saying, like for example, if I have RPM, so if I had set point, my set point, we said that we want to be at 200 RPMs, right? And then let's say that my process variable, so my current RPM, so current RPM, it's equal to 100. Then my error, that's going to be the difference between the set point and the process variable. So 200 minus 100, that's equal to an error of 100. Like this. So in here, let's say that our set point, so the value that we want to reach is 200 RPM. And then let's say that my process variable, so the current RPM that I'm reading is 100. And then the error is just basically calculating the difference between the set point and the RPM, which is 100. So the values that are going to be changing here, the set point is not going to change. What it's going to change is the process variable. The process variable is just going to be, measuring itself every loop. And then as it's going to be changing, then my error is going to be changing as well. So my error is just going to be moving depending on how much my process variable approaches a set point. And once my process variable reaches a set point, then my error is going to be 0, which means that we have basically reached our goal. Hopefully these concepts were clear on understanding set point, process variable, and error, because we're going to be seeing these variables a lot in the code as well. Okay, so now that we understood how this relationship on calculating an error works, now we're going to get into the math of the PID controllers. So I had to make a small bracket in here saying that this is not simple. So this is a bit tricky, and I actually took like a control system class in university. Like I think that was last semester, and it was really hard. I will let you know like a bit at the end. But right now, I'm just going to explain it as simple as possible with really cute drawings and really cute graphs. And hopefully I can explain like what I know to you in more simple terms. Because to be honest, when I first learned about like all of these, it was really complex for me to understand. So I'm just going to explain it to you the way that I understood it. And if you have any questions, please don't hesitate to ask around. So PID will always try to maintain error of 0, right? Yes, that is actually a more accurate representation. Yes, thank you for answering. Yeah, awesome. So for PID, we're gonna be starting with the P. So if you see, we have 3 constants. Well, we have 3 letters in here. So the P, the I, and the D. So I'm gonna be starting with the P, which is the simplest one. So P controller is proportional controller. So if you know a bit of math, you will know that proportional is just basically adding a constant to something, right? So the concept, and you can see a P controller or a proportional controller as the harder that I push, the harder that it will push back. So that's why I place like the 2 hands like struggling in there. Because if I push really hard, then it's going to push back harder. In your robot, the behavior that you will be seeing is that the output is directly proportional to the error. That's why there's a straight line in there that's proportional to the error. And the larger the error, the larger correction. So if we go back in here and seeing our error formula, so if I'm using a P controller, so a proportional controller, if my error is like super big, so like almost really like super big, then my correction is going to be like bigger. And then if I have a really small error, then I'm just going to do like a small correction. And the formula that we're going to be using is this one. So P out, or the P controller, is a proportional output. And then KP is proportional gain. So this KP is only a number. So that number like can be 0 0.1, 0 0.2, 0 0.3, depending on how you are tuning your PID. So that is just like a constant. So KP is a constant that I'm going to be determining in my code. And then ET, that's a current error. So ET is always going to be this formula. So the error that we're calculating, which is just the difference between set point and process variable. And I also added in here like set point minus process variable. So from this formula, from the P controller, all you gotta know is this, is this formula. So my constant times the current error. And the current error is just set point minus my process variable. And the larger my error, the larger the correction that I'm gonna make. So P controllers are actually the simplest ones that you can implement. So there's no need for you to, you're not always going to be implementing like the whole PID. You can also have variations of PI, PD, or just the P. From my personal experience, if you're working on like a smaller robot and your ground is just basically like there's almost no friction and basically like a controlled environment, I will only apply a P controller because there's not much correction that you're going to be making. So for example, if you just wanted to go in a straight line, maybe I will only apply a P controller because I know that it's going to be like a controlled environment. All right, and then moving on to the next type of controller, so the integral controller. For the integral controller, yes, it has to do with an actual integral from math. So the concept or the analogy that you can see is that if you are still not getting there, I will push harder over time. And the behavior that you are going to be seeing in your robot is that the output is proportional to the accumulated error over time. This might be a bit confusing, and it might give you a bit of a bad throwbacks from your math classes. But if you know the integral that we're calculating the integral, and if you go back into remembering what an integral is, it's just basically the area that we have in the curve in here. So that's why we have like this small triangle in here that's shaded. So that's the integral that we're calculating. And if you have like a small persistent error, that's basically going to be a growing correction. Yeah, I'm not sure how to explain this a bit better, but hopefully the analogy like is like good enough. So if you're still not getting into the set point that you want, so the 200 RPMs, you're going to push harder over time in order to reach your goal. So that's why in here, there's like this person pushing like a box and there's like a clock ticking because you really want to get to your end goal, but you're not still there. So you want to keep pushing until you reach like your end goal over time. So in here, we're actually implementing an important concept, which is time, right? So for the formula that we're going to be using, the output is, the integral output, which is the value that we're going to be calculating. And then the Ki, that's the integral gain. That's another constant that we're going to be defining. So 0 0.01, 0 0.2, 1, 2, 400, whatever. So that's just going to be a constant that the person doing the code, it's going to define. And then we want to multiply that times the accumulated error over time. So again, if we remember what error is just basically my set point minus my process variable. Great. So yeah, and we do need to calculate the integral there. So it's just basically calculating the integral of the error over time. If you want to see it, if you prefer a more math explanation, that's just the math explanation in there. And then finally, we have the D controller, which is the derivative. And yes, it also has to do with derivatives in math. So the concept is that if you are approaching the target, so my set point too fast, I will start pulling back early. So this is actually a really nice picture in here. So if you're driving a car and you see a stop sign like far away, you're just going to start braking. So when you reach the stop sign, you don't pass it. So you like brake smoothly. So like slow down smoothly until you reach your stop sign. So that's the same with the derivative controller. As you are approaching the target, you will start like pulling back early, so you don't like crash and like miss your target or your set point. The behavior on a robot is that if your output, so for example, the RPMs is proportional to rate of change of error, um, this can basically cause like oscillations on your robot, which will make it like, tweak like a lot. So if you're doing like the self-balancing robot and your error is like changing rapidly, then your robot is going to be like, like moving really like oscillating a lot, right? So rapidly changing error. So if your error is changing too often, then you want to do a really large correction. Um, I'm not sure. So if your robot is like falling too much, then you want to correct that like at a large scale, which is just logical. Like if your robot is falling down, you want it to correct to like make it more correct so it doesn't like fall down. And then for the formula is just we calculate the derivative output, and we have again another constant, which is the derivative gain, and that constant is basically a number. Again, it can be like 0.2, 0.3, whatever number the programmer wants to set. And then we're going to multiply that times the rate of change of the error. So basically the derivative of the error. So again, the error is on this formula in here, that is the set point minus the process variable. Okay, so any questions about PID controllers? Because right now we saw them separately. So we saw the P controller, which is the harder I push, the harder I push back. We saw the I controller, that if you're still not getting there, you will push harder over time in order to reach your set point. And then we also saw the D controller, which is basically if you're approaching the target too fast, you will start pulling back early so you don't like do overshooting like on your graph. And then now I just want to show you how it looks like in an actual graph. So if you were to plot like this behavior, you will be seeing something like this. So in here, we want to reach the set point. So the set point is basically the black line dot like in there, like, the lines that are going like this. So that's a target or set point. And if you see like all of these lines, they're trying to reach that set point. So like, for example, the first one, the red one, it is oscillating a lot. So it's doing like this. So we don't want our robot to oscillate a lot, because if we're doing the self-balancing robot, it's just going to be like this, like the whole time. And we don't want like my robot to be moving like really badly, right? So oscillating a lot. So that means that we have too much PI and not enough D. Why? Because if we don't have enough D, that means that I'm not approaching the target like smoothly. So that's why it's oscillating a lot and the graph looks like really bad. And then, for example, the overdamped, that one takes forever to reach the target. Like, for example, the blue line in here, there's too much D and we have a low P. If we go back, P is just basically the harder I push, the harder I push back. So if I don't have enough P, then I will just take forever to reach my target. That's why the graph is like really like, ooh, and then like reaching the target like really, really slowly. So if I were to relate that into my robot, that means that my robot, if I like push it, it's just gonna like fall down and then like slowly correct it. But it's gonna take forever in order to correct the error that I just caused, and it's just gonna be like super slow. And then for the perfect PID graph, it's this green line in here. So this one reaches the target fast and zero oscillation. So it's just like, whoops, and then like reaches the target like really fast. If you see the target is like the strip line, target or set point in there. And that's just example that we saw of the man like with the self-balancing robot that was like straight. The man did this and it just corrected and corrected, right? So there's no oscillation, it doesn't take forever, and it's like it reaches a target really fast and with no oscillation. So that's just basically how the graphs look like, and how the PID like have relations between themselves. And yeah. This is very interesting stuff. Thank you. Thanks for taking the session, Jocelyn. Yes, for sure. No worries. Okay, so now it's time to actually see like how they relate. And please don't be scared of this slide. Like there's too many content in here. And to be honest, I'm also overwhelmed by this slide. But if I were to like summarize everything on how a PID works. PID is just basically like adding the P plus the I plus the D. If you see in here on this formula, I'm just adding the P, the proportional term. I'm adding the integral term, and I'm also adding the derivative term. So my final like controller is just going to be equal to P plus I plus D, just like this. But in here, I wanted to place like all of the math equations so you could remember like what it actually means. So remember that KP, KI, and KD, they are all constants. So these can be changed. And then the UT is my actual result. So this UT is what I'm gonna be inputting like into my motors in there. But you can basically just summarize it like this, summarizing like all the formulas that we've seen. So summing like the P plus the I plus the D, that's equal to UT. And if we go back to my control output in here, that's basically the signal that I'm going to be sending to my system in order to correct the error. So if I go back to the example of my self-balancing robot, I'm like reading the errors, and then once I calculate my PID, this, if let's say that I do this and like my robot is like this, right? So the signal that I'm going to be sending back in order to correct the error, that's going to be the sum of P plus I plus D, and that's equal to UT. And UT is basically like just the correction, right? So we're going to be calculating that PID like every time that we see like a disturbance. So basically checking for the error really often and then just calculating the PID in order to send that correction system signal back to the system. Let me go back. We have a question in here. I've heard that a rite of passage for robotics is balancing a weight from 3 robot arms attached to each other. Can you explain why that is? Rite of passage for robotics is balancing a weight from 3 robot arms. I'm gonna look that up because I'm not picturing that. Like, wait, how can I look that up? Like to see how the setup looks like. Huh. Yeah, because I've never heard that, so that's why I'm 3 robot arms. Oh, you mean like the robots that have like different axes and like how they work? Because that's the only thing that I'm seeing here that pops up. But yeah, feel free to clarify your question so I can like understand it a bit better. Okay, so this equation is just basically like the math formula. But if you see like an actual Python code or C++ code, like you're not gonna be calculating like the integral and the derivative because that's just like not possible. So the way that we do this is that we implement it differently using like time in here because we can measure time in our program. So we're just going to be using time in order to calculate like all of these constants. Is there a reason why there is a different variable instead of t in the formula of I? No, that's just tau, but it's the same. No worries. I mean, it's okay. Okay, so this one is the algorithm that we're going to be calculating right now. So discrete PID implementation. This one is the actual code that we're gonna be seeing today, and this is how the loop works. So we have, of course, our starting point, and then we read our set point and my process variable. So again, the set point is the RPM or the variable that I want to reach, like my end goal, and then my process variable is what I'm calculating, like every time I loop. After that, after I read those variables, I'm going to calculate the error. So again, the error is set point minus process variable. And then I want to calculate all of my PID terms. So my PID terms are P, I, and D. So P is calculated K, my constant, times the error. Then the I is calculated like this, and then the D is calculated like this. To be honest, when doing like a PAD, usually I just have like a class, like a library that I always use, and then I just like call my implementation, because this is something that you will only be needing to do once, and then once you have like your library or your code for your PAD, then you can just reutilize it for like basically everything. And then after calculating those terms, you're gonna calculate the output, so P plus I plus Z. Then you're gonna apply that signal to the system, and then basically just wait for the time for every step, and you do the calculation like over and over again. So hopefully this diagram was a bit more helpful for you in order to understanding like how they actually work. But yeah, I guess I'm gonna give a short minute break so you can see this diagram and understand it. And if you have any questions, feel free to drop them on the chat. I'm just gonna go grab a glass of water, and then we're just gonna come back. And once I come back, we're gonna be seeing a bit of how it relates to motors, and then we're also gonna be seeing like this example in there. All right, so we are back. Let me see if there's any questions. We don't need to read the set point on every iteration, just the process variable, right? Kind of. I mean, you're gonna be basically reading the set point like every time, just because you are calculating the error every time. That's the only difference. But your set point is just gonna be like a base, so it's just gonna be a constant that you define in your code, and what's gonna be changing is the error that's basically being calculated like every time. So in a way, yes, you are reading the set point like on every iteration, just because you need to calculate the error on every iteration. Hopefully that was helpful for you. Okay, so let's move on now to another section. This one is also closely related to PID controllers, which are encoders. So before getting into what an encoder is, we need to first understand what is a PWM signal, which is basically how we control motor speed. So the problem with regular motors is that they only have two states. So you can either just turn them on or you can just like turn them off. So if you just turn them on, it's just gonna be like spinning in there, but like there's not gonna be a purpose in there. So it's just gonna be like, you know, yeah, it's just gonna be like it's just gonna be on, but you don't know how fast it's going or like how it is actually working. So for the solution for that is using PWM signals, and this is just basically turning that on and off very quickly in order to average that to run at a slower speed. So if we see in here, we have like these graph that says like on this one, if we leave the motor on for a really like long time, it's going to spin faster. And then if we leave it on for a really short time, it's going to spin like softly, right? So in there, we are basically calculating our duty cycle. So a duty cycle is basically the percentage of time the power is on. So in that way, we can play around with the turning on and off, but we can get like actual control of speed just by how I turn on and turn off my motor. So this is just to understand the PWM signal graph. So it's just basically like a square, it's just like going like this. And the graph shows how the voltage that we applied rapidly switches between high and low states. And the average voltage that we get in there is determined by the duty cycle. So if you were to plot a PWM signal, it will basically just look like this. And if you want your motor to go faster, then of course you will need to leave your motor on for a longer period. And if you want it to go slower, then you just turn it on for a really short period and then just like turn it off. And that's how it's like changing in here. So turn on, turn off, turn on, and turn off. And it just changes from state from 0 to 1, and like that's how the graphs is working. For these, you just basically want. I mean, you're not gonna be needing like a PWM like directly for PID, but it's closely related if you want to understand like what we are gonna be measuring like in our code. Hey, did you answer my previous question? Sorry, I went to hydrate. Yes, I actually answered that. No worries. So for this question, it was just basically me saying that you don't need to calculate your set point every time, but you are like calculating it because you are calculating the error every time. So if you see in here, calculate error, set point minus process variable, we are actually calculating that error every time that we are iterating. So even if you don't want to calculate the set point every time, you need to do that because your process variable is changing like every time. Hopefully that answers your question. You can also like watch the recording because I explained it a bit better on the first explanation. But yeah. Right, and then I'm gonna be skipping this one and just, okay, I can leave it. So this is how motor encoders work. So motor encoders is just basically like if I go back, all the way back into here, this is how a real motor encoder works. So if you see, we have like we have like a small round black object in there. That's the encoder. And that encoder, it measures like the ticks per second. So it's just gonna be like bumping the motor. It's gonna be causing like some ticks, and that's how we're gonna be measuring it here. That's how we measure the RPMs. So this is the actual mechanism. To be honest, I don't even understand this like really well. I just know that the motor, it basically causes like these ticks, and with the ticks you can calculate like the RPMs that you're getting. We can see it better in here. So encoder output pulses. So the encoder basically generates a series of digital pulses as the motor rotates. So this graph shows the pulses that is generating. So high, and then goes low, and then goes high for a longer period of time, and then low again. So each pulse corresponds to a specific angle of rotation of my motor, and the speed of rotation is determined by the frequency of these pulses, and the total rotation is found counting them up. So by having the ticks of my encoder, I can actually calculate my RPMs. So that's my way of measuring something. And again, if I go back to the beginning, the only way that you can correct your error is by measuring your error. So these component that's called encoder, it's going to allow us to count those pulses in order to calculate my RPM and then determine my output. And then here is this is a better explanation on how these motor encoders actually relate to PID controllers. So number one, the encoder provides feedback to the PID controller. So basically the encoder is the feedback loop that's going to be, sending out how much RPMs we have. And then it will measure the actual speed and position of the motor as well. And then the PID controller will calculate the error between the target and the actual values that it's measuring from the encoder. And at the end, it's going to adjust the motor's power, or which is just a PWM that we already learned what a PWM signal is, in order to minimize the error. And if we see in here on this diagram, we see that the output signal is the pulses, so the ticks of the encoder of the black disc. Then we have our PID microcontroller, which outputs a PWM signal. And that PWM signal, which is the output, is the one that goes as input for our motor. So if we want to reach the 200 RPMs that I was mentioning earlier, I need to calculate the RPMs using the pulses of this encoder. And then I'm going to be reading like 120 RPMs, 200 RPMs, and so on until I reach the target. And that input signal, it's going to generate this PWM signal that goes directly into the motor in there. That is just going to adjust the motor's power, which is the PWM, in order to minimize the error that's going on in there. Okay, so with that, we basically just finalized all of the technical concepts that I wanted to cover. Again, I know there was a lot of content that was explained today, and please, these things are explained through time, and they require time to understand. I did my best at explaining them at a really like broad glance, but don't hesitate to research more about them. Ask Gemini, or you can also ask me directly on Discord, or watch the recording again. Hopefully with the activity, you will see how everything simples down to code. I'm also going to be showing you a real life example of a robot that I built, and how it has like its internal PID. It actually has two PID controllers. So I'm going to be showing you that as well. And then we're going to do a quick activity on Tinkercad so you can see the simulation and like try it on for yourselves. At the end, the only way of understanding these is by actually doing the code and knowing how it relates. So hopefully by seeing some examples, you will understand like how these variables and how these formulas like actually come to life. All right, so in the meantime, I'm going to show you that example that I promised about. So I'm just going to go to my GitHub. And then I'm going to show you that. Let me search it in here. Okay, so this one is basically, let me let me show you some videos. Okay, so this is the robots that we basically built. I mean, it's not exactly these ones, but it's in the competition that we participate. Let me show you the videos. Oh. Okay, so these are the robots that we coded. Not exactly these ones, but they are similar. And if you see the robots, they have omnidirectional wheels, so they can basically move, like translate themselves into the XY plane in any angle. And in order to calculate that angle, you need a PAD controller, because I mean, there's no way of knowing that you reach like 90 degrees angles without like actually calculating something. And then the other PAD is for the speed of approaching the ball. So if I have my ball in here and I have my robot, I don't want my robot to like crash the ball and just like run over it. So with my PAD controller, I can actually decrease the speed over time. So when I reach the ball, it reaches like gently. And this is just how, these robots are like interacting in there. So you can see like how they actually work with the ball in there. Okay, so this is a code for those robots. If I go in here, I believe it's main. Yeah. So in main, I have my class that's called PID. So if I go to PID C++, which is the code that we're using, we see in here that we have a definition of all of the constants. So my constant for proportional, let me make this bigger. My constant for integral, my constant for derivative, my error, the last error, and the last time calculated, which is just the milliseconds of the last iteration. And then if I go down in here, I'm going to explain this later, but in here, well, wait, no. In here, if you see, I'm calculating the error, right? So set point minus input. And this function, it receives a set point and it also receives an input. So in here, I'm just calculating the error. I'm doing some stuff in there. And then for the proportional, I'm calculating all of the outputs in here. So proportional, it's my constant times the error. For the integral, is my constant integral times error times delta time. And then for derivative, which is the last one, is my constant derivative, error minus last error divided by delta time. And at the end, my output is just the addition of all these variables. So proportional times integral times derivative. And at the end, what I'm returning is the output here. So if I go back into the code in here, let's see an implementation of this PID controller. So in here, I'm initializing my PID class and I'm adding all of the constants, right? So my constant P, my constant I, my constant D. And then for using the PID, let me see. In here, I'm calculating the PID.calculate. I'm passing on the set point and also the input. So set point is basically the angle that I want to reach. And then the input is the actual angle that I'm reading. So in here, my rotation angle is my goal. So the angle that I want to reach. And then the B and O angle is the angle that I'm reading from this EMU sensor, which is called B and O. This is a type of sensor. And then with that, I basically get my speed omega that I need in order to like how much I need to rotate my motor in order to reach this desired rotation angle. And this speed is the one that I actually like add into my motor so they can actually like move and rotate. All right, so I'm gonna send you this code in here in case you wanna see this application of a PID. And you can literally just copy paste this class into your robot and it will basically work. I mean, at the end, it's just a function, right? It's a function that receives a set point and an input. and then the constants, right? So there's nothing else. And if you can see, it's just 33 lines of code. I mean, this is a whole PID controller implementation in here, and it's super simple, and you can also use it for Arduino as well. Right, so now it's time to actually see our own simulation. So let me remove this one and move on. So for these, we're gonna be using Tinkercad. I actually wanted us to build the circuit from scratch, but for the interest of time, I'm just gonna be showing you like the circuit itself, and then I'm gonna be, going through the code and explaining like each of the things that are in there, and then I'm also gonna be sharing that simulation so you can also run it and see. Keep in mind, I was doing these a bit in a hurry, so it's not working like really good. But I will share you the project so you can like work on it as well. And if you like manage to make it work like really good, you can send it to me via Discord. So that will be like really nice. Okay, so we're going to be using Tinkercad. Tinkercad is just basically a workspace, and I can share you like the link so you can create your accounts in case that you don't have one. But you don't need an account to run my simulation. It's like over there. So there it is. It's this one. Tinkercad is basically a platform that allows you to create circuits and run them live. It's like creating simulations of circuits. And there's other things that you can do. You can also do a Scratch, like code blocks, like on Scratch. And you can also do like 3D design, like if you like CAD designing for like mechanics, mechatronics, or all of those careers, that's also allowed in Tinkercad. But the purpose the tool that we're going to be using today is the circuits one, because we're going to be doing like a circuit. So let me remove this one and add this one. So we're going to be using this slide simulation, and let me actually send you this. I'm not sure how to send these. I'm not sure. Okay, this might work. I'm going to be sharing you this live in here so we can all be like on the same page. I'm not going to be going into like all of the specifics of these circuit, but basically in here we have some basic components which we only really care about my motor. So this is a DC motor, and if you can see, it has an encoder. So encoder is already connected in here, and it's DC motor with encoder. We can see it in here. It has different pins that we need to connect, and in this case, we are going to be using these MOSFET in here. It's an N-channel MOSFET. It will allow us to like load the power of the Arduino in order to control like the high power motor, which is this one that we have in here, using an external 9 volts battery source. The battery source is this one. This one is our power supply in here, and then we are also using this diode in here that is placed across the motor terminals in order to protect the circuit from some dangerous like voltage spikes that can be caused by the induction of these. And finally, the encoder, which is already built in our motor, it's going to be sending the real-time feedback pulses, which is the pulses that we already talked about, to the Arduino, which is this one, to a specific Arduino interrupt pin. In this case, we are using the pin number 2 for that, and that will basically enable the PID algorithm in order to calculate the exact RPMs, so the revolutions per meter, and adjust the PWM output instantly. Yeah, I already shared these with you, so you can check like all of the circuit, and I believe the code is also in there. I asked Gemini to add comments to it, so let me just check if they're like accurate. So first thing that you need to do on every code is do the pin definitions. If you want to learn a bit more about the Arduino syntax, feel free to watch my previous stream on Arduino, introduction to Arduino, so you can see like how everything works. So in here, we're just defining the MOSFET pin and the encoder pin. And then I created a variable that's called encoder ticks. So those encoder ticks are the ones that we're going to be getting from rotating my motor. So the encoder that's built in my motor, it is going to be generating like these ticks. So we want to make sure that we are generating those. And then at the end, then I'm setting up my PID constants. So my set point, I want to reach 500 RPMs, and then I am defining my constant proportional, constant integral, and constant derivative. Again, these are just numbers that we can plug in. After this explanation, I'm going to be showing you how you can tune these PID constants. There's different algorithms that you can use, and there's a whole like math thing like behind how to tune PID constants. But for robots that are like simple, I usually just do them manually and by eye, just like by looking how my robot behaves. So I'm just, adding these ones, but like keep in mind that these ones should change and you should tune them like properly. Then I have some variables in here, such as the current error, previous error, the integral sum, and my derivative. So that we're going to be using in order to calculate everything. We also need some timing variables, such as my current time and my previous time. And then something really important that I forgot to mention is my loop interval or my sampling interval. So this interval is going to be how often we're going to be running my PID loop. So how often, it's going to be calculating like everything. Why? Because at the end, PID relates to time because we have the integral and we have the derivative as well. So we want to make sure that we are using like an appropriate sampling rate in here. And then I'm just doing some configuration of the encoder in here. That this is related to Arduino. And then on the loop, I calculate my current time. So I'm going to be using this millis function, which basically gets the current time in milliseconds. And then I want to run the PID calculation every 50 milliseconds, which is what I define here in my loop interval. So if my current time minus previous time is greater than or equal to my loop interval, which is 500 milliseconds, then I want to do like all of these things that are in here, which is just basically calculate the PID. So the first thing that we want to do is calculate the RPM, so my process variable. So to calculate that, we use this formula in here, and then we want to calculate the current revolutions. In here, this is a formula that's used. This is also another tricky section because you need to know your motor's pulses per revolutions. Usually, this is something that you calculate by hand, or you can also approximate them. So in here, I'm just assuming that we have 300 encoder ticks per one revolution. So in order to know how many ticks are in each revolution, what you need to do is that you just turn your motor on for one revolution and then just count how many ticks you get. And then you just calculate the current RPMs, which are encoder ticks divided by the ticks, and then you just multiply. Using this formula in here for getting RPMs. This is a fixed formula that you can find online. This is not something that I invented. This is just something specific. We have a question in here. DT is delta time? Yes, on line 41. Yes, you are correct. Yes, delta time, because we are calculating current time minus previous times, which is delta. Then reset counter, previous time equal to current time, and then we are entering the PID zone. So we calculate the error. So current error is set point minus current RPM, and the RPM, we are calculating that from here, so double RPM. And then for the PID, for the P, we do my constant times the current error, which is this one in here. Then we do the integral sum in here, which is this one. So a constant integral times the integral sum, and then derivative, right? So derivative is KD times my derivative. And at the end, I just do the final output signal calculation, which is P plus I plus D. And then this output signal is the one that we're going to be inputting into our motor. So actuate motor, right? So analog right, my pin, and then my output signal that I'm converting these into an integer. So this output signal is the RPMs that are going to be inside my motor in there. So start simulation, and then we can see, the RPMs and how they are changing in here. So the output signal are the RPMs that go inside the motor in there. And then this is very important, save the errors for the next loop. So you need to make sure that you do this, because this is a loop and you're going to be iterating until for every like loop interval, so 50 milliseconds basically. All right, so this is a simulation in there, and what I need to do, I need to calculate the RPMs correctly, because right now I think that is failing, specifically this section for the ticks, because we need to know how many ticks are on this encoder in order to calculate the PID correctly. So if you figure that out, feel free to reach out so we can check it. To be honest, I didn't have enough time to check these, because I had to do like the circuit and then like do the code and slides and everything. But hopefully this is a really nice template that you can use for your projects. And I also shared this one with you. This one is a bit cleaner because it has a nice class and everything with a method that you can use in order for it to work. And yeah, then let me go back here. Also, I already shared like both links with you, like the Tinkercad project, and then I also shared like my PID class that I did for the soccer playing robots. So let's move on. Okay. So this is the circuit that we were basically building. It's just basically like the circuit that I show you that you can also access on the Tinkercad in there. And yeah, and then as I was mentioning in here, and if I go back, there are some constants in here that need to be calculated, like the key constant P, constant I, and constant D. So these ones, they are not just like numbers that I randomly like just decided to choose in here. These numbers, like they actually have a reason. So if I go back in the slides in here and move on into how to tune a PID, so there is a whole process of adjusting like the P, the I, and the D on gains of a PID controller, right? So the main goal is to optimize the system's response to stability. So basically, reach these green line in here. So the perfect PID. And in order to do that, you need to have a really nice fine-tuned constants. So it involves iterative testing and refinement, and you often start with tuning the P, then the I, and then finally the D. So if you are someone that is familiar with music, it's just like tuning a musical instrument for having like perfect pitch. So if you're someone that's very familiar with like fine tuning like a guitar or like another instrument, then you must know that in order to get like really nice notes, you need to like tune your chords or whatever instrument you're using. It's just the same for the PID. You want to make sure that you are like moving. You start with the P and then you move on with the I and then the D. You usually start with increasing the P, like for example 0.2 P, and then so like you can start so you can start with P 0.5 and then just move these to 0. And then once you realize that the P is working correctly, then you can start adding like I and then the D. From my personal experience, the P is usually the largest one, and then these ones are like super small. And there are systems that don't even require like the derivative or the integral. So usually there are systems that can behave really well just by using like the P controller. Then we have a question in here. How does the Arduino code relate to the one we saw earlier on GitHub? Is this separate code just meant for running simulation? So this one is basically like the .eno file of the Arduino. So if I were to run these, like there's an actual execution in here that's like going on. But then if I go back to my code in here, you will realize that this is these are basically classes in C++, And then I have my main.ino, which is basically this code where all of my logic is. And in here, I'm just including my PID.h library. So if you were making your own code, you can basically copy paste my library for PID and then just use that PID on your like main code for whatever implementation that you want. I think in here, let me check. Yeah, in here, this one, I'm using a sampling time for 20 milliseconds. If you see, this is my sampling time. But yeah, you can feel free to use this code for like any implementation of your choice, to be honest. All right, so let me go back. Okay, I guess I want to show you, let me see if I can find PD tuning constants. Because it's like different methods, and I remember seeing them on class, but then I just like forget. This one looks nice. This is basically like a PID, a block diagram of a PID controller of how it works. If you see like the P and the ID are being like added in here in order for the output. And this is a formula that we just saw like earlier. This is nice. Okay, so here are the different methods. So manual tuning is what I was just basically mentioning you. So you start with 0 point something on the P, and then on I and D you leave like 0, 0. But there's other different methods. There's also the Ziegler-Nichols method. I believe this one is by using like the graph in order to do stuff. Let me look this up to see the graph so you can see. Usually, like the tuning of the constants is the hardest part of the PID. If you want to be someone that does like things correctly, you are going to tune your constants correctly. But if you just want to do it fast and like work decently, you can just fine tune them by trial and error. Yeah, so this one is just basically calculating like these constants, like these Ziegler-Nichols first method. All right, so I guess with that, we can definitely wrap up our stream. I'm going to share this link for feedback on the chat. It's basically feedback about the stream, what you like, what you didn't like. If you want to see something on new streams or different streams, that's something for you to take into consideration as well. Hopefully you really enjoyed this stream. I really enjoyed like making all of the content. Remember that if you have any questions or you are building a project and you want some feedback about it, feel free to reach out via DM. I'm always open into hearing your opinions and anything. I believe I will be making one more stream on embedded systems. That one is also going to be related to robotics, and we're going to be seeing basically how assembly code works in computers from scratch and how embedded systems like actually work. It's going to be a short stream, so definitely feel free to drop by and ask any questions. I believe that one, it's going to be, let me just check the schedule really quick. I believe that one's on Monday, but I'm not really. Yeah, that one's on Monday. It's going to be at, I think it's 7 p.m. ET, but it's also on the schedule. It's called Embedded Systems, and it's going to be a clear introduction into embedded systems and seeing how everything works like on the backside. If you want to also learn more about Arduino, feel free to see my previous stream of this Global Hack Week, so you can get to know and understand like this presentation a bit better. Other than that, that was everything for me today. It was my pleasure having you, and I will be seeing you soon on Monday. Bye, everyone.